The first lesson in this unit is going to cover how to graph exponential functions. So we're going to look at two different kinds of exponential functions. We're going to look at growths and decays. They're exactly what they sound like. A growth is one that is going to increase as your x values get larger. Your y values also get larger. So the function is growing. A decay is the exact opposite. As your x values get larger, your y values decrease. So that's why we call it a decay. Some different parts of an exponential function. You're going to be looking at things that look like this. So for example, something like y equals 2 times 3 to the x power, or something like y equals 1/2 times 4 to the x power, or something like even y equals 3 times 1/2 to the x power. So we're going to look at a lot of different kinds of exponential functions. The things that make an exponential function an exponential function is the fact that the powers now are all variables. So we're coming off of a unit where all of the powers were numbers like 2 or 3. So we're looking at things like x cubed, x to the fourth, and so on. Now, rather than having a variable base and a number power, now they're flip-flopped. So now we have number base and variable power. So when we look at exponential growths, they're going to have this same general pattern. The nice thing about these curves is that exponential functions always look the same. So we're coming off doing some different graphs about rational functions where they all looked different. And we had all kinds of different weird things we had to find in order to help us structure what they looked like. That's not true with an exponential. An exponential function is always going to have this same general shape if it's a growth. So what makes an exponential function a growth? The number being raised to the power, the b there, has to be a number bigger than 1. So if I have something like y equals 2 times 3 to the x, since that 3 is the number being raised to the power, since that power is bigger than 1, that means, that base is bigger than 1, that means that the exponential function is going to grow. So it's an exponential growth. So we're going to look, and as you see, as we go bigger into the x's, the y values go up. So some characteristics about it. Number one, this x-axis acts as a horizontal asymptote. So if you remember with what we talked about in the last unit, as this curve falls down to the left, we're going to approach the x-axis, but we're actually never going to cross the x-axis. Some other things, these two special points that we're going to graph. Whenever we graph these, we're going to make tables of values to graph them, but we're only going to worry about doing tables of values for 3 different numbers. So every single time you make a table of values, all you're going to be required to do are tables with -1, 0, and 1. And they're very, very easily evaluated with an exponential function. So take this one for example. If we were looking at 2 times 3 to the x, if I plug a -1 in, -1 does not change your number to be negative. It changes it to be a fraction. So 3 to the negative first is not -3. It's 1/3. So you'd be taking 2 times 1/3, which is 2/3. If you plug a 0 in, 3 to the 0 is 1, just like any number to the 0 power is 1. 2 times 1 gives you 2. We throw a 1 in. 3 to the first is 3. Multiply by 2, you get 6. So you can see as your x values get bigger, your y values start increasing, and they start increasing at a faster rate. If you wanted to do another point like 2, 3 squared is 9, and 2 times 9 gives you 18. So look at how much of a jump we have in between all of these numbers. Exponential functions grow very quickly. Things that we're also going to talk about, domain and range. With an exponential function, the nice thing about these is that you can plug in whatever number you want. So your domain is always going to be all real numbers. Your range here totally depends on your horizontal asymptote. So in this case, since the horizontal asymptote is at 0, that's why this says that the range is greater than 0. The other type of exponential function that we're going to look at is an exponential decay. So these are all decays. So an exponential decay happens when that b value is a number that's less than 1, but bigger than 0. So a number like y equals 2 times 1/4 to the x. This would be considered an exponential decay because the number being raised to a power is less than 1. So notice that as my x values get larger here, my curve falls as I go towards the positive x's. That's why it's called a decay. So as I look at this, the entire curve falls. Similar characteristics. We're going to approach the x-axis here, but never actually cross it. So the x-axis acts as an asymptote. To graph these, we're going to follow the same 3 table of values. So we're still going to graph -1, 0, and 1. So plugging in -1 into this specific case, -1 here, 1/4 to that power is not -1/4. It would flip the fraction upside down. So 1/4 to the -1 is actually a value of 4. Multiplied by 2, you get 8. Throw in a 0. Anything to the 0 power is 1. Multiply by 2, you get 2. Throw in a 1. 1/4 to the first is a 4th, times 2 gives you a 1/2. So as you see, as the x values get bigger here, the y values start to decay, they start to fall. That's why this is called an exponential decay. Domain and range, just like a growth, all real numbers, you can plug whatever number you want into this power and you're not going to have an issue. Range always depends on your horizontal asymptote. Since the x-axis in this problem is my horizontal asymptote, that's why we're saying the range is greater than 0. What we're going to do is we're going to graph some different functions that look a little different. So first thing you're going to do in every single one of these is you are going to graph the parent function. So what's going on without any shifts? So in this problem, I'm graphing y equals 3 to the x power. So we're going to make an xy table for that graph, and the values we're always going to pick are going to be the same, -1, 0, and 1. And all we're going to do is plot each one of these points. If you put -1 in, remember it doesn't make it -3, it makes it 1/3. If I put 0 in, anything to the 0 power is 1. I put 1 in, 3 to the first is 3. So if I graph what this original parent function looked like, I'd be at -1 and a third, 0, 1, and then 1, 3. If you wanted to go further and plot another point, you can. If you plot 2, 3 squared gives you 9. So notice that the curve starts to grow very quickly. Now as I draw this, this portion is going to skyrocket, and this portion is going to follow the x-axis out forever because the x-axis acts as an asymptote. So how are we exactly going to graph these? Just if this is a little light on your thing, that's a +1 there. So we're going to use our rules of transformations. So whenever we see a number added or subtracted on the end of a function, that's going to take you up or down. In this case, since it's positive, it's going to take you up 2. Anytime we see a number added or subtracted with our x value, that's going to take you left and right. Remember our rules of transformations. A +1 is actually the opposite of what we would think, and that goes to the left by 1. So what we're going to do is take this table of values we already created, and we're just going to shift each one of the values using those 2 transformations. So let's do that. If I go left 1, every one of my x values just gets 1 subtracted from it. So we'd be at -2, -1, 0, and 1. Every one of my x's just gets 1 subtracted because we're going to the left. My up 2 just takes and adds 2 to all of my y values. So my 1/3 becomes 2 1/3, my 1 becomes 3, my 3 becomes 5, and my 9 becomes 11. So not only has the entire curve shifted up, but so has my asymptote. My asymptote is going to shift with my graph. Since I went up 2, That means my new horizontal asymptote is also going to shift up 2. So we're going to be at y equals 2. So when I go to my graph, dashed line at y equals 2, that's the new line that my curve is going to approach but not cross. Plotting my points, we go to the left 2 and up 2 1/3. We go to the left 1 and up 3. We're at 0 and we're at 5. And then the last point's a little bit off the graph. It's up at 11. So looking at my curve, if I connect the dots, notice that the shape of the curve hasn't changed. The only things that have changed is that it moved to the left by 1 unit and we pushed it up 2 units. Last thing you're going to determine for any graph is your domain and range, and we're going to do that of only the shifted function. So only the purple one. So if I find the domain, remember any exponential function is all real numbers. And then my range is from horizontal asymptote and up. So my horizontal asymptote is at 2. So we're going to go from there to infinity. Not including the 2 because we're never going to cross that asymptote. We're going to take and do the exact same things for this next one. The only thing that's going to be different, notice the number that's being raised to the x power is a number smaller than 1. So this problem is going to be a decay. It's going to fall as we go to the right. We're still going to use the same values. So I'm going to start off with -1, 0, and 1. If you want to continue to add more numbers, you can, but these are the 3 that I'm going to require. Now, when I put in -1, remember that that doesn't change this to be a negative number. It changes this fraction to flip upside down. So this flipped upside down is 2. Multiply by 3, you get 6. Throw 0 in. Anything to the 0 power is 1. Multiply by 3, you get 3. 1/2 to the first is 1/2. Multiply by 3, you get 3/2, which is the same thing as 1 1/2. If you want to plot 2, you can. If you want to plot 3, you can. You can keep going as far as you want. I'm not going to. So as I plot these, -1, 6, 0, 3, and then 1, 1 1/2. So knowing what we know about the general shape of these, all that's going to happen is as I go to the right, this graph is going to fall and then continue on and follow the horizontal asymptote. Making our new table, we're going to look at our 2 transformations. So again, anytime you see a +1 with your x, any plus value is going to move you to the left. Anything that's subtracted or added on the end is going to move you up or down. So this is going to go down 2 in this case. So all I'm going to do is take my table of values that I have here, and I'm going to move left 1 by subtracting 1 from all of these. And I'm going to move down 2 by subtracting 2 from all of the y's. So subtracting 1 here, we get a -2, a -1, and a 0. Subtracting 2 from all of my y's, I get a 4, a 1, and a -1/2. The last thing you need to realize, since the whole curve is going to go down, my horizontal asymptote is going to go down also. That always comes from whatever your shift here is. So since we went down 2, my horizontal asymptote is going to be at -2. Plotting my points, -2 and up 4. Then I'm at -1, 1. And I'm at 0, -1/2. So notice that the general shape of where those dots were didn't change. The shape of my curve isn't going to change. The only thing that's changed is we've gone left and we've gone down. Domain and range. Domain for any exponential, all real numbers. Range is always based off your horizontal asymptote. Horizontal asymptote at -2, and we go up from there. So from -2 to positive infinity. You'll have several practice problems like this on your worksheet for homework. The next part of this gets a little abstract. So we're going to talk about this number called e. E is called your natural base. It's a numerical value. So if you go to your calculator or you're looking at a calculator, such as the one I just put on the screen, notice my calculator has this E button directly above the button that says natural, or LN. We haven't talked about what this button means yet. Okay, that's your e to the x. So if I turn my calculator on, and you can do this on any calculator that you have, if it's scientific, if it's graphing, and so on, if I push second and the ln button, notice that it gives me e to some power. So if I just do this as e to the first power, because that's anything to the first power is itself, notice the numerical value that it gives me. Now look at your paper, or look at the note sheet here, and it's the same numerical value as what the calculator is telling me. E is just a number, just like pi is just a number. So if I go to my calculator and I push the pi button, notice that it gives me the value of pi. Same thing for E. E is just a number. E gets used a lot in applications of exponential functions. That's why it's relevant. We're actually going to use it later in this video. So where does E come from? E comes from taking that expression and making n as large as we possibly can. So if I take this expression and I plug in a 1, and then I plug in a 2, a 3, a 4, a 5, a 6, then I start plugging in bigger numbers like 10, 100, 1,000, a million, a billion, a trillion. The higher this value gets, this n and that n, your calculator is going to start telling you that you're approaching this never-ending decimal. So this, again, is going to come back in applications that we're going to do about interest. So that's the relevance of E. Now, if you graph E, you can graph y equals e to the x the same way that you'd be able to graph y equals 2 to the x. E is just 2.72 approximately raised to the x power. So if I made a table of values, you could come up with a table of y values just like we did in the exponential growths that we already did. So E is just a numerical value. That's probably the hardest part for students to get over is, oh my gosh, what do I do with this E thing? It's just a number. E is just approximately 2.72. So when I'm asking you to graph something like e to the x, all I'm really asking you to do is graph 2.72 to the x power. When we talk about it in decay form, notice that it's e to the negative x. Here's the reason why. If I change that power to be positive, the entire fraction would flip upside down. So you'd have 1 over e to the x, and it would look like this. So notice that the number being raised to a power is a fractional value less than 1. It's the same thing as if I asked you to graph 2 to the negative x. If I wanted to change that to a positive power, it'd look like 1/2 to the x. So the number being raised to a power is a number less than 1. E acts the same way as every other number acts. It's just a decimal value. It's just nicer for us to use this letter E rather than have to write out this nasty decimal every time, just like it's easier for us to use the pi symbol rather than write out that nasty decimal every single time. I have some sheets in here where we could graph E. We're going to skip this. I'm not actually going to make you graph it. What you need to understand about this, though, is that it acts the exact same way. Since this is an e to a positive power, it's going to look generally something like that. Since this one is e to a power, but we're going to the left and down, it's going to look something like this. So same growth pattern. It's just we have a number in here that's a decimal, 2.72, rather than having it be 2 to the x or 4 to the x or 6 to the x. But it's the same exact concept. So why do we learn about E? That's where we get into this issue, compound interest. There are two different types of interest. There's simple interest and there's compound interest. So what's the difference between the two? Simple interest is found by using the equation I equals PRT. So the interest that you earn is your principal amount multiplied by the rate that you earn interest at times the amount of time you leave the money in the account. This is called simple interest for this reason and this reason alone. The only thing you're earning interest on is the money you initially invested. So if I invest $5,000 and I get an 8% interest rate, I'm earning $400 in interest. Now here's the deal with simple interest. That's the most amount you're ever going to earn in interest. You're never going to earn more than $400 every single year that you leave the money in the account. So simple interest is called that because the amount of interest you earn per year is the exact same amount every single year. Compound interest is different, and the reason why it's different is this. In my first year, I'm going to earn interest off what I invested. In my second year, not only do I earn interest off of my initial investment, but I also earn interest off of the interest I earned. So in year one, in this scenario, I would earn $400 in interest. In year two, however, I'm not only going to earn interest off of the $5,000 that I earned, I'm going to earn interest off of the interest that I also earned. So the money in my account is $5,400. So I'm going to earn in the next year $432. Then in the third year, not only do I have the $5,400, but now I have this extra $432. So now I'm earning interest off of $5,832. So in the next year, I earn even more interest. So compound interest, it's called that because you continue to compound how much money you earn interest off of. So what happens is the money in your account grows at a faster rate than what simple interest does. Now there's two kinds of compounding. There's compounding where you can count the number of times you compound. So this would be something like when you see the words monthly or daily or quarterly. That's when I earn interest 12 times a year. I earn interest 365 times a year. I earn interest 4 times a year. This continuous equation comes into play when you don't know how many times you've earned interest because it's like a continual clock. So I always relate this back to the world population clocks. If you've ever seen a digital world population clock, it tells you how many people are in the world at any given time, and if you've ever looked at one, the very last number on the clock continues to roll forever. It never stops rolling. So what you can think about continuous compounding is, if you looked at a clock or a digital readout of how much money was in your account, the last few numbers on your clock for your account, they'd never stop spinning. You're continually earning interest for every millisecond that your money sits in the account. So the difference between the two, this one, you can count the number of times that you're earning interest, and in this one, you're continually earning interest, so it never stops. So what do all these letters mean? In both equations, the P is called your principal. That's how much money that you put in initially. The R in both of them is your rate, so what's your interest rate? Things that are important, your rate has to be a decimal. Don't try to stick 6 in for 6%. It needs to be 0.06. The T is always your time periods. When you're doing interest, T is always going to be in years. And then in this one, the N is the number of times you compound. So if I'm doing monthly, these N's would be 12s. If I'm doing daily, the N's would be 365s. If I'm doing quarterly, the N's would be 4. If I'm doing yearly, I'm earning interest once a year, the N's would be 1s. Okay, so let's do a problem here. It says you inherit $150,000 from a relative and you decide to invest the money for 5 years. And you have 3 options. Here's option 1. You're going to earn 6.85% interest, there's your R, and you're compounding quarterly, there's your N. So let's talk about a couple things. Your rate needs to be a decimal. So 6.85%, 0.0685. Please don't say it's 0.685. That is 68.5%. If you can find an account that's going to pay you that much interest, please let me know what it is, because I'm going to put every cent I have into that account. Okay, so make sure that your decimals is correct. So my T here is 5 because it's 5 years, and my initial investment is the $150,000. So I've got everything I need, so we're going to plug into my first formula. P is 150,000 times 1 plus 0.0685 divide by n, which is 4, and we're raising to the 4 times 5 power. So that point, once you have everything put in the formula, everything is going to the calculator. So all I'm going to do is plug all this stuff in the calculator. Now be careful that you know how to plug this stuff in correctly. I usually do this step by step. I usually do the fraction first, 0.0685 divide by 4. Then I add the 1 to it. Then I raise it to the power, so it's to the 20th, 4 times 5. Then I multiply by the outside number, 150,000. So in my account at the end of 5 years, I should have $210,657.94. Please don't use the 3 at the end. This is dollars and cents. You're not going to have 94.3 cents in your account. Flipping to the last problems. How would this change if I'm talking about a different interest rate and we've got a different compound? So now my rate has changed, 0.067. Daily, I'm now compounding 365 times. So same formula, 150,000 multiplied by 1 plus 0.067, divide by 365 this time, and it's 365 times 5 power, NT. Again, calculator. Fraction first. Take that, add 1. Take that, raise it to this power. So I'm going to put this in parentheses, 365 times 5. If you don't put that in parentheses, your calculator is going to raise it to the 365 power and then multiply the whole answer by 5. So you want it to multiply first, then do the power. Then I'm going to take that number and multiply by my investment of 150 grand. And I get a little bit more money, I believe. This is 209,000. Oh, I lied. It's a little bit less. 684, and it's 61 cents. You might be thinking to yourself, wait a minute, I earned interest more times. Why is this amount less than the last one? What you're going to figure out really quickly is that the amount of times you compound is actually way, way, way less important than the interest rate that you earn. The better the interest rate, the more interest you're going to earn. Last one, we're going to do the continuous one. So in this case, now my rate has changed a little bit more. And we're compounding continuously, which means we're using the other formula. So we're going to do A equals PE to the RT. Remember, the P is my 150 grand. The E is a number. I am not going to change it to a decimal. My calculator has an E button. So there's no reason to round it, just like we don't round pi to 3.14 anymore. We're past that. We use the pi button. We're going to use the E button in the calculator. And then the rate, 0.065 times 5 power. So I'm going to take this, throw it in the calculator. So we've got an investment, $150,000. Second ln key gives me my E, 0.065 times 5, close the parenthesis. So my calculator, exactly what I have written down, and I get a little bit less even still, $207,604.60. So again, even though we're earning interest forever, never stopping earning interest, notice that my interest rate was less, and that affected my money even more than the fact that I earned interest more times. Okay, that better interest rate is your better goal. Make sure you write down any questions that you have and ask them in class.